good afternoon, everybody. My name is Stanislav Popelka. I'm from Palacky University, and today I will tell you something about eye tracking in cognitive cartography and the story of our department and our research during the last decade. I will start with very short introduction about myself. So that's me on the photo, and I'm from Department of Geoinformatics, Palacky University in Olomouc. Olomouc is a city in the eastern part of Czech Republic, as you can see on the map. And I have a background in geography, geoinformatics, and cartography. And I'm working with eye tracking since 2011, when we bought our first device. And in that year, I started my PhD. So I started working on eye movement research, and since that, I'm working on that. And currently, I'm working here at our department as head of eye tracking laboratory, but our laboratory is quite small, not because of technologies and equipment, but because of personnel. So that's me and my PhD student and some undergraduate students. So we are a very tiny group, but we are trying to do our best. And the laboratory looks like this. It's equipped by SMI 250, that was our first eye tracker, and Tobii Spectrum 300. We got some eye track trackers and pupil core glasses, and we try to combine eye tracking with EEG, so we got also some EEG device. So that's our laboratory, and my today's presentation will be divided into 3 parts. In the first one, I will give you very basic introduction into the area of cognitive cartography. Then I will showcase our studies, or I selected few studies that we did to show you which kind of visualization methods and analytical things we are using. And in the last third part of my presentation, I will try to introduce you some tools that we developed at our department to analyze and visualize eye tracking data. So I think that all of you know what the cognitive or cognition is, but cognitive cartography can be, according to Montello, divided into 3, let's say, research streams. The first one is map design research, which aim is to improve maps. So that's what we basically do. We are trying to improve maps. So we develop, let's say, 2 versions of map, and we are trying to find out which one is, let's say, better or more readable by participants. Second stream is map psychology research, which also use maps, but not because of not to improve maps, but to understand something about human cognition. And the map is just the tool, like reading studies use text. So this kind of studies use maps. And the last stream is map education research to improve education process with and about maps. Yes, and at our department, we are, as I said, we are focusing on the first one, but we also cooperate with psychologists on the second one, and with didactics on the last one. Yes, and map design research is part of usability studies, so we are doing usability of the maps. And now I will move to history of cognitive cartography. First cartographic studies were done in 50s and 60s of last century. And the milestone was the release of the book called Look of Maps, which was about cognitive aspects in cartography, because before that, the cartographers were focusing only on history of cartography and this kind of stuff. And since 50s, they are focusing their attention to the cognitive aspects and design aspects of maps. And the period between, let's say, 75 and 85 was like the golden age for map design research. And I found somewhere that more than or about 30% of articles, scientific articles in cartography, were devoted to user aspects. So let's say 1/3 of all researchers work on user aspects. But then digital revolution appeared, and it means decline of interest in cognitive research, because geographic information systems emerge and people start to focus on how to create maps automatically. And they, let's say, overlook the cognitive aspects. But then in 1995, another important book was published called How Maps Work. And it again triggered an interest in cognitive research on design and interpretation of maps. And the interest is still there. And Now something about eye tracking in cartography. The first eye movement studies were obviously conducted in other fields than cartography, like reading, psychology, and this kind of stuff. But study of Enoch from 59 was important for us because he conducted several experiments aimed at interpreting aerial photographs. So aerial photographs and maps are somehow similar. And then White and Ford studied target seeking behavior of 6 respondents on simulated radar screen. So the radar screen is also something like map. But the milestone in our area was symposium influence of map design. Influence of map user on map design. Map design from Ontario, Canada. And one psychologist called Leon Williams presented here his eye tracking research about something in Honeywell company, and one of the attendees of the symposium was George Jenks, cartographer, who decided to focus his research on eye tracking based on this talk at this symposium, and he started with that. And as far as I know, this is the first cartographic eye tracking output from 73 from Jenks. And the left side shows some kind of scan path. On the right side, there is something like attention map, yeah, but not with colors, but with the grid density. And now I'm moving to the present. Some Chinese guys, especially Wang et al., in 2016 wrote that article that summarizes all of Web of Science articles found by keywords like eye tracking, cartography, and something similar, and they visualize the results in the pictures that you can see in the presentation, and you can see that our department or our university and myself are highly visible there. So we are doing a lot of research in that area. And similar article from Krasarakis and Cybulski from 2019 summarizes again studies from cartography and eye tracking, and they showed there the number of studies during last, let's say, 10 years, and you can see the increase. For my book, I did something very similar. The numbers are not the same because I use maybe different keywords, but the trend is there that let's say from here is the decline because of automatization in cartography. But let's say in the beginning of new millennium, the number of articles increases, and it's still increasing. And what is more important from this article is this graph that shows the areas where the studies were published. The first one is cartographic symbolization design principles, so how to do the maps. Second one is comparing 2D and 3D representation, which was my PhD study to evaluate 2D and 3D visualizations. And then map users expertise, so similarities and differences between different groups of users like expert, novices, cartographers, non-cartographers, etc. And what is important, eye tracking analysis tools and methods delivered by cartographic community. So relatively large number of papers were devoted to the development of tools for eye tracking data analysis and visualization. Yeah, because our area is about visualization in maps, so it's quite similar. And the last part of my presentation will be about the tools that we developed. So now I'm moving to the second one, which is showcase of cartographic eye tracking research that was conducted at our department. And on this screen, you can see different pictures from studies that we did during the last, let's say, 10 years, from some studies with driving wheel, when we analyze human behavior with GPS navigation simulated in some computer game. This is from 3D visualization from my PhD thesis, and in cartography, this visualization method is quite often used. It's called space-time cube, when time is displayed in Z direction or in Z axis. So it shows, let's say, time and space together. That's why it's called space-time cube. And we did some studies with eye tracking glasses as well, and we evaluated also some web maps, and we played with EEG also. And my dissertation was, as I already said, about 3D visualization. So I prepared 7 eye tracking experiments on different aspects of 3D visualization, from perspective or pseudo 3D visualization, from perspective views to some thematic maps, hill shading, and let's say city maps or maps of urban space. And it was, let's say, at least in Czech Republic, it was first study with eye tracking in cartography, and also in, let's say, European area. It was one of the first, let's say, complex studies on this topic. And now I would like to show you, let's say, 3 or 4 studies that we did, from very simple, like this one, when we compare, let's say, static images or scans from old roadmap atlas. It was based on cooperation with Cartography Praha, which is the biggest Czech cartographic publishing house, and they are publishing these roadmap atlases, and they are still used. Even that people have GPS navigations in their cars, they're still buying these roadmap atlases. And the publishing house has old one from 1997, and then, let's say, new one from 2013. And they got feedback from their customers that the old one was better, the roads were better visible, etc., etc. And we want to analyze if it's true or not based on eye tracking research. So we conducted a study when we proposed some tasks, and participants had to found something in the maps, and we found that the old one is, let's say, more usable or more user-friendly to the participants. So and what is important, based on insight from our study, they improved their atlas, and in 2018 the new version was published, and it incorporates the changes that we proposed based on this study. This is also, let's say, similar study or on interactive maps. So we used 3 interactive maps depicting some geographical things like transportation and I don't know, number of crimes in Chicago. The maps were developed by our colleagues from Pilsen University, from western part of Czech Republic, and we analyzed, let's say, screenshots like here, screenshots of the first, let's say, front page, to analyze where the first fixations go, and also, as I said before, that sequence charts are important for us. So we analyzed in which time they assess which areas of interest of the front page, and then in final step we analyzed the interactive work with the tools to find some problems of the visualization, and again our insights were incorporated into final version or next version of the maps. For example, this one on the video is used in Pilsen for traffic modeling. And this is, let's say, contemporary work from last year, where we evaluated COVID dashboards. So there is some connection to the previous presentation. And we started with existing COVID dashboards. We chose these 4, where the map is, or the spatial information, the map is dominant, and we analyze it by eye tracker, and also with by questionnaire and some interview. So, for example, from the interview, this shows, let's say, positive and negative feedback from users. And based on this insights from this study or from this testing, we proposed new version, or 2 new versions of COVID dashboard on a case study of Catalonia. We call it light version and dark version. And then again, we perform another study where we compare these two dashboards and find out if the light version is better than dark version. And again, we used sequence charts to analyze the order of, let's say, visited areas of interest. And this is, I think, the last study that I picked for this presentation, and it was, let's say, the most complex and most time-consuming, because here we used, let's say, interactive maps again and areas of interest. But the problem was that users interactively work with applications, so each participant turn on and off the legends, or here moved with let's say swipe visualization, which was let's say time-consuming to draw areas of interest manually, because as you can see here, as he moved with the swipe, we have to change the size of areas of interest interactively, and it took a lot of time to do that manually. So I spent a lot of COVID marking this areas of interest. But finally, we got information about dwell time in each part or in each area of interest of the maps, and then I transformed that in this form of this sequence chart that was unfortunately done mainly manually, because the output from SMI that offers sequence chart is not perfect with interactive data. So I have to combine data from multiple visualizations, and it was a lot of manual work. So I spent again many hours working on this kind of images. But finally, I think it offers a lot of information, and we can look to data and interpret what happened during the work of the participant. And that leads me to the last part of my presentation, that will introduce you the tools that we use for analysis during our research. I propose you, let's say, I showed you, let's say, four studies, but we did a lot more. But the visualization and analytical methods are relatively repeating, and we are using software from the vendors of eye checkers like SMI and TobyPro. We did a lot of research in SMI because we have a lot of experience with that. It's our first device, so we are familiar with that. And when we bought TobyPro in 2017, the functionality of TobyPro Lab was not great. So but it's better and better. So now we are, let's say, switching from SMI to Toby. And what is important, we are using OGAMA, which is open source software developed at Berlin University many years ago, and it's stopped to be developed in 2015, but it's still working, and we use it a lot. So we develop some kinds of converters from SMI to OGAMA, from Toby to OGAMA, from gaze point to OGAMA, because it offers quite nice features comparable to these ones, and students can use it at home, and it's we like it. And another software that we use is called Analytics. It's geographic information system developed for spatial temporal data, which are eye tracking data are also spatial temporal, because there is space in XY of the screen and time. So there are some features that are nice to be used for eye tracking data. So again, we got some converters to this Analytics. But my presentation will not be about these simple converters, but I would like to focus on our, let's say, flagship, which is ScanGraph. Because as I tell you before, as I proposed before, we are comparing maps, so simply two variants of maps, but sometimes we would like to analyze similarity in stimuli reading between groups of participants, like cartographers, non-cartographers, youngs, adults, etc. So for that, we developed this online tool ScanGraph, which is freely available on this page. And it reads data exported from OGAMA, SMI Gaze, and TobyPro Lab. so from all eye trackers that we need or all softwares that we are using. And it works or based on ScanGraph comparison, which is based on ScanGraph theory from Newton and Stark from 71, and it uses a string-array distance method. So imagine that this is a ScanGraph recorded over the map, and this gaze trajectory is replaced by character string according to AOI hits. So in that map, we, let's say, mark these 3 areas of interest and replace this complex line with the sequence of letters representing AOI hits. So this one was AA, B, C, C. Yes, and if you have more participants, you have more sequences, and you can compare these sequences. And these sequences are then, their similarity is calculated based on one of 3 algorithms, which are listed here. And this is how the software looks. And I would like to very briefly show you the interface, which looks like this. The main window shows these, let's say, points, and each point is one participant. Yeah, and the color of the points represents categories of participants. So in that study, we got, let's say, three categories of people, which differs in color. And those who are connected by lines are those who are similar to some level, and the level can be defined by a user. So now this is 99% of similarity. So they use exactly the same strategy of stimuli inspection. So their order of visited areas of interest is exactly the same. But if I want to show those who are similar at least to 80%, I can do it like this. And now those who are connected are similar to 80%. And if I zoom in and click to the edge, I can see that, for example, these 2 are similar to 87.5%. And what is, let's say, the most important part of this interface is the part on the right side, when you can see, let's say, the groups of participants that are similar to each other. Yes, so all of these are similar to all the others in the group to at least 80%, because my parameter is 0.8. Yeah, so I can see that this group is completely similar to each other, and I can see their names here, and the last, yeah, and I can see here at the bottom their sequence of visited areas of interest. So these ones used something like B, C, D, A, and it's not exactly the same because it's on 80%. So this one used something very similar, and etc., etc. And the final thing is this CSV export. So I can export, let's say, the raw data or the similarity data. This is original metrics calculated based on Lindemann-Wunsch visualization. This Lindemann-Wunsch algorithm. This is normalized values. So, for example, E15 and A2 are 0.6, similar to 0.6 or 60%. And at the end, I have the groups here, and these are my input data. So input sequences of areas of interest, sequences of fixations in areas of interest. And so I think that's all from this. You can select the method here, and this collapsed, non-collapsed means if you are counting repeated fixations in one AOI or not. Yes, if not, the similarity is higher. So that's the reason why I see these nice groups here. And now I will go back to my presentation and show you some more functionality. In this case, we calculated the average similarity of the participant towards all the others in some group. This study was some didactics of physics. So physics teacher divided his students into 3 groups. Let's say minus, those who are not good in physics, average, and good ones. And this visualization or this analysis shows us those who are least similar to the others, so they are not belonging to the group, so they were assigned to this group by teacher by accident, or it's not based on true, because they are not similar to the others. So we highlighted those who were badly assigned to the group. And this is much more complex study. When we analyzed behavior or eye movement behavior of 30 students and their geography teacher. So again, we got similarity metrics, and we calculated by Levenstein distance in ScanGraph, but we also used multi-match, which calculates similarity not based on order of fixation, not based on fixations, areas of interest, but all based on the shape of the scan path. So we calculated the similarity among students. This is the yellow part. The similarity of the teacher towards the students, which is the blue part. And then after some calculations, we found the tasks where teacher used completely different strategy than the students. So this visualization shows that students are connected to the group and the teacher is out of there, because as you can see from here, students look to the legend, look to the map, and the teacher look to the completely different part of the map. So from that reason, she was, let's say, not connected to the students. In contrast, in task 02, is this one, the teacher looked to the similar places as the students, because they look to the Africa and to the legend here. And you can see that she's connected here to them, and we can quantify this similarity and says if she used unique strategy or common strategy the same as the students did. Yeah, and I got the last 2 minutes of my talk, so I would like to very briefly introduce you two other softwares or tools that we developed. The first one is called ET2 Spatial, and it's for analysis of interactive maps. Because if participants work with interactive maps, each of them works with map in a special way. So they move with the map, zoom in, zoom out, and it's quite hard to compare participants if they look to the same places or not, because eye tracker records in coordinates of the screen. And we developed a tool that converts these screen coordinates into the coordinates of the map, into geographic coordinates, so we can display the fixations in geographic coordinates in the map. And finally, we can have multiple scan paths in the map, like it will be, or like it would be recorded on static image, but they were able to zoom in, zoom out, and pan with the map. And finally, if we got data in our geographic information system, we can analyze them by some geographic or GI methods. If you are interested, you can check the QR code. We wrote some paper about that. And the very last slide of my presentation is about software or tool which is under construction now. It's called Gaze Plotter. And as I mentioned many times in my presentation, that sequence charts are, let's say, important for us, and only software that allows their generation from eye tracking data, as I know, is SMI, but it's not perfect. It's like raster image, and there are some other problems. So one of my students is now working on, let's say, interactive web-based tool called Gaze Plotter, which can which you can interactively change. You can highlight something. You can click to the fixations to display some more info, and you can turn off, turn on some areas of interest. So I hope that after, let's say, 6 months or something, the tool will be finished, and we will use it with advantage during our research. So thank you for your attention. I know that it was quite fast, but I want to show you as much as I want, and I'm happy. I will be happy to answer your questions and discuss our research. Thank you.